Hello everyone. Today in the digital communication lab experiments, in today's lab experimental video, we are going to discuss about differential phase shift keying. That is experiment number 8. So we have already discussed about phase shift keying in the previous lab video. In today's session, we'll discuss about what is differential phase shift keying, that is what is DPSK and compared to PSK, how it is different from PSK, and how to generate DPSK modulated signal or modulated output, and how to demodulate that. So all these things we'll discuss in this lab session. But before that, I'm going to review the theoretical concept of DPSK first. After understanding how DPSK working or how DPSK modulation is generating, then only I will move on to the experimental analysis. So let us start the discussion of differential phase shift keying. First, I will discuss about the DPSK modulation process from this block diagram. So as you know that this is what the block diagram for DPSK generation or the modulation. Now, all of you carefully observe the difference between PSK and DPSK. Here, if you observe the terms or name, PSK is differentiated or compared with DPSK, there is a term called differential. That means somehow differential data is generating in DPSK. That is all the difference between PSK and DPSK. Now we'll see what is the meaning of this term, why it is added to this PSK. Okay. The first thing, all of you observe that why we need to perform this DPSK experiment. Sir, what is the advantage of DPSK when compared to PSK? Because we have already PSK is existed, but why we are going for DPSK? Why we are modifying the PSK design so that it will generate DPSK signals? Because in PSK, if you want to demodulate this PSK signal, definitely you should go for coherent detection process only. So there is no other way to demodulate PSK. So because of that, the major disadvantage of demodulating the PSK signals is we need to use coherence carrier in the demodulation process. So in the coherence carrier means we need to maintain perfect phase and perfect frequency in the demodulation process. That means the carrier used in the demodulation that must have same phase and same frequency with the carrier used in the modulation process. For example, here in the modulation process, the carrier signal is used having some sinusoidal waveform. It is having some phase and frequency value. So this same carrier that must be used in the demodulation also. That must be used in the demodulation also. Whenever we are using a coherent detection. For example, simply the coherent detection is nothing but multiplication of the modulated waveform or modulated signal with the coherence carrier. Okay, so this is the simple representation of coherent detection. So whenever if you find a term called coherent detection, then in that coherent detection you can clearly observe this particular block first. So in the demodulation of coherent detection, the modulated signal has to be multiplied with the same carrier. That means the carrier used in the modulation. So the same carrier must be used here. So this carrier and this carrier must be same with respect to frequency and with respect to phase. But if there is any phase deviation between this carrier and the carrier used in the demodulation, then definitely there is some changes in the demodulation, and also there will be some errors in the demodulation of the PSK if you don't maintain this same coherence carrier. So it is concluded that the maintenance of the same coherence carrier in the demodulation is very difficult in case of coherent detection. That's why without the use of this coherence carrier in the demodulation, so in a non-coherent way, we can able to demodulate the PSK signals. in a non-coherent way. We can able to demodulate this PSK signals. Okay. So the process of non-coherent way of demodulating the PSK signals is sometimes called as DPSK. That means DPSK can also be considered as a non-coherent version of PSK. So to eliminate the drawback of maintaining same coherence carrier, we can able to go for DPSK. Of course, the output is same. That means in PSK, whenever the input is 0, we will get 180 degrees phase shift from the carrier, and whenever the input is binary 1, we will get the 0 degrees phase shift as the carrier. So the same kind of phase changes will be obtained after DPSK also. So same type of output is generating, but without the need of coherence carrier and the demodulation, we can able to generate and detect the DPSK signals. That is the main advantage. And another advantages of DPSK compared to PSK is the bandwidth is going to be reduced when compared to PSK, and also the implementation is somewhat accurate, right? So because of the advantages, we are going for DPSK modulation compared to PSK. So let us observe this block diagram. So in this block diagram, if you clearly observe this particular block, which is mentioned as a green indication, this is nothing but PSK modulation process. That means in PSK modulation process, the input digital data, that is ones and zeros, first it will convert into NRZ level encoder. So after NRZ coding, each one is going to be represented with +1 volts as an amplitude, and each 0 is going to be converted into -1 volt. That means alternate positive and negative pulses are going to be generated after this NRZ coding. So after that, simply this is going to be multiplied with the carrier signal. Here balance modulator is simply multiplier. So this data is this +1 is multiplied with C of t, you will get C of t. -1 is multiplied with C of t, you will get minus C of t. So one is having same carrier, in other case we are having negative carrier. So negative carrier or negative signal means out of phase, that is 180 degrees phase. We already observed in the PSK generation. So that means in PSK, whenever the input here, this is what the input for PSK process. If the input is 1, we will get same carrier, but if the input is 0, we will get 180 degrees phase shift in the carrier. So like that, we observe in the output as two different phase variations. That is what PSK. But how DPSK is generated means, in addition to the PSK, some more logic analysis, some more logic circuit is added here. How it is added means, so instead of directly applying the input to this block, we are modifying this input to another form. So this form is called as a differential data. That's why this is called as differential phase shift. So that means actual input data is going to be converted into differential input data, and based on the differential input data, the PSK outputs are generated. That is just very simple process. But here we need to observe how actual input is converted into differential data by using some logic circuit. Generally, the logic circuit used is XNOR gate. As you know that a gate, XNOR gate, is having two inputs. So one input is the actual input, other input is nothing but which is taken from the output and passed through some delay element, so that previous value of the output. So delay means getting the previous value of this present output. So from this output, the previous value is taken as the another input to this logic circuit as XNOR gate. So one of the XNOR gate input is input binary data, and other input is delayed version or previous value of this output. For example, here 0 is generating at this moment. Then what is the value here? The previous value of 0, that is 1, is coming here. So all the previous values are generating as another input, and present input values are on these two inputs. XNOR as this one, the Boolean representation. So both input B of t and delayed previous value D of t minus TB, both are first XOR, and then if you make the negation, it will become XNOR. Only after generation of this differential data, then directly apply to the PSK process, so that two phase changes you can easily observe. Here I'm not going detailed into the PSK because we have already discussed about PSK process and PSK lab experiment also. So same thing is happening here. But only the difference between DPSK and PSK is how to generate this differential data. That is the thing, right? Now we'll move on to the experimental analysis. So all of you carefully observe this hardware kit. Number of times I have mentioned this particular kit because in this kit you can able to perform the experiments on ASK, FSK, PSK, DPSK and so on. But here our goal is to perform an experiment on DPSK, differential phase shift keying or differential binary phase shift keying. So let us observe only this part. So that's why after pressing this modulation selection switch, we can able to enable any of the modulation technique. But in our case, pressing the switch and enable this differential phase shift key, modulator and demodulator. So if the LED is on means, so only this part is enabled. Other modulation techniques are disabled. Okay. And also in the previous lab sessions I have explained all these things. So this is what the data. We can select input data as 8-bit or 16-bit or 32-bit from this particular switch. Similarly, the clock signal frequency is also be selected based on this switch. Generally, we can select clock signal frequency as 2 kHz. Okay, or if you want to change that, you can press this switch and change the frequency of the clock. So as you know that every digital bit sequence, for example, if you select 8-bit data as input, if you want to observe how many bits or what is the bit pattern of this 8-bit, that means how many ones are there, how many zeros are there in this 8-bit input data, then you should definitely compare this bit sequence or this waveform with clock pulse. Then only you can able to observe what is the corresponding bit sequence. So that input data is generated after this bit coding. So for this modulation, this is the input. For this modulation, this is the input. For this modulation, this is the input. So all the input data is coming after this coding. Okay. For example, in our case, this part is nothing but the DPSK modulator, and this part is nothing but the DPSK demodulator. First, we'll observe what is the input here at this particular pin. All of you observe that in this particular kit, Scientech kit, no need of any connections. You can directly observe the intermediate outputs and actual input and outputs, and you can easily analyze. So if you connect the CRO probe here, you will observe input. If you connect CRO probe here, you can observe clock. So clock and input are compared so that you can able to observe what is the bit sequence. Now all of you carefully observe, there is a logic circuit is mentioned here as compared to the block diagram. Here you can consider this XNOR gate. So there are two inputs to the XNOR gate. One of the input is actual input data, other input is taken from the output as a delay element. That means the previous value of the output is connected here. So the XNOR gate output is generated at this 18 pin. So this input or this output is nothing but the differential data. So that differential data is connected to general PSK block. So general PSK block means just by multiplying the carrier signal will generate two phase shifted waveform of modulated signal. That is considered as a DPSK. And the same demodulation can be observed directly at this particular thing. Okay. Now, of course, here it is used the coherence carrier, but generally a DPSK is used for detecting the signals in a non-coherent way. Okay. Now let us see the experimental analysis. This is what the procedure. Anyway, I am explaining the procedure step by step, so we need to read all these things. Right. The first step is observe the input while comparing with the clocks. Here, as an example, here I am taking 8-bit data as the input. So this is what the input, and this is what the clock. So here, while comparing the time period of the clock, so during this one clock time period, if you observe there is a high pulse, then you can consider that as a binary one. So I'm taking it as binary one. Next clock time period. This is what the next clock time period, starting from here to here. During the next clock time period, again I have observed that high pulse is coming. So again we should consider as again one. Now next. During the next clock time period, low pulse is coming. So that means you can consider as 0. So again low pulse 0. High pulse during only one clock time period, so only 1. So 0, 1, 0, 1, 1, 0, 0, and so on like this. So this pattern will be repeated. So if we clearly observe the sequence, some 8-bit pattern is repeating. So what is the 8-bit pattern which is repeating here? For example, if you start anywhere, you can start from anywhere and observe 8 bits. So that will be repeated. Here I am, as an example, I am starting from this particular point. So 1100 1010. Okay, 1100 and 1010. Starting from this to here, there will be 8 bits. So you can clearly observe this 8 bits is again repeating from this. So again 1100 is appearing here and it will be repeated. So that means this is the procedure in order to observe the corresponding bit sequence in the input data pulses, right? This is only happen whenever if we compare the clock signal time periods, right? This is the first step. Second step is observe the differential data when compared to the clock signals. So again here compare the differential data pulses in compared to the clock time period. If the clock time during this clock time period, if you observe it is 1 high pulse, so you can note it as 1. Again high pulse means 1. Again high pulse means 1. Otherwise 0, 0, 1, and so on like this. Okay. This is the way to observe bit sequence when compared with the clock, right? I will explain the procedure in the video. And before doing an experimental analysis, first of all, we should observe the theoretical comparison as theoretical output. Okay. So as you know that this is what the XOR gate or XNOR gate. Actually, this is what XOR gate. If you make a NOT operation after this, this will be XNOR. Okay. So one of the input is direct binary input. Direct binary input. What we are applying here, and other input is which is taken as a delayed version of the XNOR gate output. So that means some output is generating here. So we need to make one time period delay. So that means the previous value is obtained here. Okay, which previous value? The previous value of the output. This one. The previous value of the XNOR gate output is obtained as another input. So based on this logic operation, here I am going to observe what is the XNOR gate output. They use XOR gate also instead of XNOR. So that is also given here. For example, this is what the input sequence. As an example, this is also observed from the waveform. Our waveform here. For example, in this waveform, our input is 11001010. Here also, I can clearly observe somewhere else that is repeating 11001010. So let us take the sequence, continuous sequence, as the input, and let us assume the previous value is 1. So let us assume the previous value is 1, and here the present input is 1. So 1 and 1, if you make an XOR operation, that will be 0 because same inputs are coming. So output is 0. So automatically XNOR will be 1, reverse. Like that, if you perform present and previous value with XOR operations between this, you can clearly observe. So 0 XOR with 0, 0, 0 XOR with 1, 1, 1 XOR with 0, 1, and so on. This is the XOR output. If it is XOR gate, this is what the output you can able to observe as the differential data. Here, where is the differential data coming? This is what the differential data in the kit. Okay, this one. At this particular pin, if you observe that in the CRO, then this is what the pulse waveform you observe. Based on that pulse waveform, if you observe the bit sequence, so this will be the bit sequence if this gate is considered as XOR gate, and if this gate is considered as XNOR gate, this is what the corresponding bit sequence. You in the experimental analysis, you can clearly observe this bit sequence because the gate is a XNOR gate. Okay. Now in practical, we'll try to observe this all the XOR operation and DPSK output. Then the third step is observation of DPSK output when compared to the differential data input or data input. So whenever the input is 1, automatically the same carrier is producing here. You can clearly observe same carrier. Whenever the input is 0, you can clearly observe there is a negative carrier. So carrier is reverse. So reverse means 180 degrees phase shift. So here there is 0 degrees phase shift, and here during this portion there is 180 degrees phase shift. That means the phase of the carrier is going to be changed between two values whenever the input combinations are changing. So that's why this is called as phase shift keying, but it is the modulation is generating based on differential data. So that's why it is called as differential phase shift. After observing the modulated output, so you can observe the demodulation output. So when I compare with the input, so demodulation and original input must be exactly same. Clear? Now here I am going to explain the direct experimental video. Okay, so all of you observe, and again I am repeating that all these experimental video I am going to explain in a play and pause mode. That means sometimes I will pause the video and I will explain, and then I will play the video. So let us see this. This is what the kit. I already said that by using this switch you can able to select any of the modulation technique, right? So here I have selected DPSK modulation kit. Okay. Now this is what the selection of data input. As an example, LP data is selected. This is what clock. So 2-place clock is selected. Now where the actual input is generating. So here this is what the clock signal. If you observe the clock signal in the CRO, this is how it will appear. You can note down the clock signal frequency and time period also. Now where the data, original data is generated from this clock, based on this clock, after the coding, so after this pin only, the original data is generated. For example, if you observe, this is a DPSK generation. At this particular pin, if you observe the CRO, you can observe the original input data, that is 8-bit data. Okay, here, right? So I'm connecting CRO probe here, and also another CRO probe is connected to clock in order to compare the data with the clock. Okay, and the remaining probe is connected to another probe is connected to ground. So make the CRO in dual mode. One is connected to input, another one is connected to data. So you can clearly observe with respect to clock signal. If you observe the data during one clock time period, if it is high, you can clearly mention it as 1. Otherwise, it is 0. So 1, 1, 0, 0, and so on. Based on this, you can clearly observe what is the corresponding bit sequence in the 8-bit data. Okay. Yeah. This is what way we need to observe a corresponding bit sequence when compared to the clock signal. So this is what input, and other input to the logic circuit is coming from output. So here I am directly observing XNOR gate output. So this is what the XNOR gate output. Okay. Now, in a similar way, you can also compare the XNOR gate output with the clock signal, and also you can clearly note down the corresponding bit sequence. That is already explained in the slide, right? Here I am directly observing the DPSK output, and also I am comparing with the differential data. So whenever it is high, automatically same phase carrier is producing. Whenever it is low, that is 0, so it will produce reverse carrier, that is 180 degrees phase shift carrier. You can clearly observe the difference, right? As like in PSK. Here, next, directly observe the demodulated output. Okay, so that demodulated output you can compare with the original input. First you can compare with the differential data, and then finally you can compare with the original input. So the both original input and differential demodulated data must be exactly same. Okay. In the previous, that is a comparison of demodulated data with differential data, and now this is the comparison of demodulated data with original input. So you can clearly observe this same bit pattern is obtained at the demodulation. This is what original input and this is what demodulated is. Okay. So for every analysis, you try to compare with input and corresponding output what we are observing. So always place two CRO probes and in a dual mode and try to compare the different analysis of bit sequences. Okay. So that's it. That is the experimental video. Okay. And these are what the observations you can able to obtain from that particular experiment. So you need to observe first the clock signal, corresponding clock frequency and time period, and then observe the input data and observe the encoded input data, and then the differential encoder output. That means that is nothing but the differential data which is coming from the XNOR gate output, and compare it with the theoretical data. I have already explained the theoretical output. So compare that theoretical output with the practical output what we are generating. So and try to observe the difference and observe the carrier signal at the TP20. Of course, we need to observe the carrier signal also, and then modulated as well as demodulation. So these are the corresponding 8-bit, 16-bit, 32-bit, 64-bit sequences which is generating from this particular kit. So that means from this particular kit, if you want to observe what is the 8-bit data, so this is what it is already given. You can compare with by observing the CRO probe, CRO screen, whether it is same or not. Clear? So that is for today experimental session, right? So thank you very much. In the next video, we'll meet. In the next video, I will make a video based on linear clock code and cyclic codes also. So for this now, thank you very much as of now.